Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will continue our discussion with some more examples, some day-to-day examples of how to calculate the work done in a conservative field. So the next example that I have in mind is that of a motion of a planet around a star. So the example is that we have a star with large mass. Remember the word large mass, because in our calculation we will see that whenever a quantity has a significantly larger mass compared to the other planet under consideration, that larger planet or star is not going to move much. So essentially that large mass star is going to be stationary in the calculation. Okay, so large mass is orbited by two planets, P1 and P2, of masses M1 and M2. So we want to find the energy conservation equation. Want to find the energy conservation equation, and for example now the forces here under consideration are due to gravity here. So we have to write down the external forces. So the external force here is due to gravity. So what we do is we assume mass of star to be m, which is much greater than m1 or m2, right? So we have two planets of masses m1 and m2. So that is given here. The large mass star has a larger mass. So now we have the planets are let me draw a little bit of a diagram so that helps me in my calculation. So we have a star. Let's say star is at some origin O, and because of large mass it's not going to move much. And we have planet number 1 and planet number 2, which are separated by a distance, let's say R1 and R2, right? These are vectorial distances. So let us say now the star is fixed at origin. The star is fixed at origin O, right? And now we have the total potential energy from external forces. The total potential energy from external forces are given by phi, which is m minus m m1 g by r1 minus m m2 g by r2, right? So the total potential energy from the external forces are given by this. Okay. So then from here what we have is the internal forces. I can write down my internal forces P1 and P2 given by H12 to be minus M1 M2 G divided by R12 square, right? So the internal forces. Okay, and now from here I can, what do we have here? These are my internal forces, and from here I can write down my internal potential energy. So from here I can integrate to find what is H12. My H12 comes out to be minus M1 M2 G divided by R12. right? So this is going to be negative of an integral of h12. Okay, so we have this external potential. So now I can write down the entire expression. So see, we want to find the total energy of the system. So I can write down the entire expression for the energy of the system, right? So what have we got is energy conservation. So half mv1 square plus half m1 v1 square plus m2 v2 square minus mg m1 by r1 plus m2 by r2, and these are the contribution coming from the external components. Remember, we treat the star to be external because, and that is why the gravitational force due to the star is the external component. And then the mutually interacting planets also have this internal components m1 m2 g by r12. So this is my total energy of the system, and that is my E. So the first two, this is the kinetic energy, and the next two are my potential energy. Okay, so these two are my potential energy. Okay. A quick question I can ask is, typically in astronomy, we talk about the escape velocity, right? Or whether a planet can escape the gravitational field of the solar system or the gravitational field of the star cluster. So this question that typically is asked in astronomy is, can the planets escape to infinity if E is less than 0, right? Now the solution is yes. If E, the total energy, E implies to the total energy. If E is less than 0, then certainly the planets can escape to infinity, but not both the planets. Why? Because we will see that if E is less than 0, so if E is less than 0, then both planets cannot escape to infinity. Both planets cannot escape to infinity, and we will see why is that. So because what is going to happen is, we have let us see in the formula itself. Suppose both planets go to infinity, right? They escape the gravitational field. Then in that case, so what I'm saying is, suppose both planets go to infinity or escape the gravitational field of the star. So then what we will have is that R1 goes to infinity and also R2 goes to infinity, and of course the planets are going to infinity, they are going to move infinitely far away from each other. Then we will have that R12 also go to infinity, and then we will have zero contribution from the potential energy, and all we will be left with is kinetic energy. So the total energy is nothing but equal to the kinetic energy of the system, but that is always positive or non-negative, and that is a contradiction because of this statement. So hence both planets cannot escape to infinity. One planet, it is possible. Okay. So now let us continue discussing the constraint system here. Right? So constraint system. The constraint system. We talk about constraint forces. Which can be external and internal, right? So the constraint forces can be external when, for example, the pulley mass system, right? A mass is constrained to move along a thread which is rolling along the pulley. So that is an external constraint on the mass. Now suppose within the mass suppose we have multiple particles within the mass, and we treat that entire particle system to be a, let's say, a single unit or a black box, right? Within the black box, we can have multiple particles which are mutually interacting, and those are the constraints which are internal constraints, right? So let me write down what I just said. So external constraint. So when a particle is constrained to remain at rest, when a particle is constrained to remain at rest, for example, by some external setup, we will look at this example. And then internal constraint forces could be when the particles are constrained to remain at the same distance, right? The particles are constrained to remain at the same distance. Let's say, two particles are tied together by a rod, and that the rod allows us to keep the two particles together. Okay, so then what we have is then in that case, the total, we talk about the ideas of the total work done. The total work done by any pair of mutual interaction forces, right? So will be, of course, the internal work. This is the internal work, right? So this is the internal work, and we see that this is 0. This is going to be 0 when the particles which are acting upon these constraints are, let's say, they remain at a fixed distance. So the total work done by a pair of mutually interacting forces is 0 when the particles on which they act are constrained to remain a fixed distance apart. Okay, so that is what we have. So we want to show that this is true. So let us keep this statement as some sort of a result, and let us try to prove this statement. So proof. So the proof is, suppose Ri minus Rj is A, which is a constant, right? And we are assuming that the particle remain at a fixed distance apart, right? So then we can possibly square this relation. So we have that Ri minus Rj square is A square. But this quantity is nothing but, I can write this in another way, the left hand side, Ri minus Rj dot with Ri minus Rj, right? So this is A square. Okay. So now what we can do is we can differentiate this relation, differentiate with respect to time, right? With respect to time. And we see that this is nothing but, this is going to be Ri, we differentiate. So this is Ri minus Rj dot with Ri dot minus Rj dot, right? But what is Ri dot minus Rj dot? So and this is equal to 0 because A is a constant. But this quantity is nothing but Vi minus Vj, right? So this quantity dot with this quantity is 0. So now what have we got here? What we see is that the dot product of the mutual distance between any two particle with its with its relative velocity is 0. Or I can write this in a more concise form that Rij bar dot with Vij bar is 0. Right? Now remember, if we want to find that work done by mutually interacting forces, so the work done W is going to be integral Gij dot with Vij. Right? And remember, the mutually interacting forces Gij is if you recall some of my previous slides, this is Hij Rij hat. So the mutually interacting forces, they act along the direction of the mutual distance, right? This is nothing but Hij times Rij bar by Rij, right? So the direction of these mutually interacting forces is Rij bar. And then when we take a velocity and dot product, here we are taking a dot product, we take a dot product, we are certainly going to get a 0, right? And that proves our result that the work done by mutually interacting forces is 0, provided the distance between the particles, the interacting particles, is constant, right? So that's a very nice and very neat result. Okay. So what have we got here from this simple exercise? We can recap our thoughts and these ideas in a following single statement. Work done. So energy conservation for a constrained system. Energy conservation for a constrained system. So when the specified external and internal forces acting on the system are conservative, right? Are conservative. We see that, and the constrained forces do not work. The constrained forces do not work in total, right? What are these constrained forces? For example, the constrained forces which allow the particles to remain at fixed distance, they do no work in total. Then the total kinetic energy plus the potential energy, the total potential energy is a constant. Okay, so we have recapped all the scenarios in a conservative field. Okay, so let us look at the application of this statement through one example. So the example is, so a ball P of mass 2m is suspended by light inextensible string. Okay, so inextensible string, and the string of length a from two sliders, okay, Q and R, and each of mass m, and they can move on a smooth horizontal rail. They move on a smooth horizontal rail. So let me write down this statement and I will draw the diagram. The system moves symmetrically about O, right? And O, which is the midpoint of Q and R, and remains fixed, right? And P moves downwards. Okay, so we want to find the energy conservation. If the system is released from rest. Okay, so then what have we got here is, so the setup is as follows. So we have two masses of mass m here, and these are, let's say, located at some points, let's say Q and R, and let us say the midpoint of the distance between the two masses is O. So that is the O which is symmetric about the two masses, and the masses, they are, let us say, they are separated by a distance x. We don't know what is this x, but let us say the masses are now tied to another mass of total mass 2m. So the tied mass is mass of 2m, and it is tied with a string of length a, right? So this is given here, string of length a, and then what we get is the total let's say the total vertical distance is z. So we have that a square, x square plus z square is a, where a is a known quantity, and at any given time x and z is changing, right? So we have to find the energy conservation of the system if the system is released from rest, right? So which means at t equal to 0 we have some initial condition, which is the resting initial condition. Okay, so now I can write down. So this question is, for this setup, the system is under set of two constraints here. The masses small m's are only constrained to move horizontally, right? And the mass capital 2m is allowed to move only vertically. So which means that there is only one, given the fact that the length of the string a is constant, we can have either two unknowns x and z, or the fact that x and z is related to a using Pythagoras theorem, we only have one unknown, which is the angle theta, and that can be our degree of freedom, right? So the system has only one degree of freedom. And let us say the distance q and p is given by these distances q and r. The q and r is given by x, which is a cos theta, and z, which is a sin theta, right? Okay, so here what we get is that from here I can find that x dot is minus a sin theta times theta dot, and y dot is a cos theta dot, right? So we have x dot and, well, z dot. These are my two velocities along the x direction and the z direction. Okay, so then from here I can write down the total energy. The total, to begin with, the kinetic energy of the system is given by T is half mz dot square. So this is for the mass 2m, so I have to put a 2m here because the mass 2m is going vertically down, and then plus 2 times half m x dot square, right? And we see that this is going to be m a square theta dot square. We plug in all these formulas for x dot and z dot square. We see that this is theta dot square. Well, we use the the trigonometric theorems, and we find that this is the quantity. And of course, now the potential energy of the system at any given time. Notice if we put that these two small masses m to be at zero potential energy, right? We will see that this large mass capital 2m is going at any given time point will have a potential energy negative 2m gz, right? Because if the zero is at this level where the two masses, the horizontal masses are kept, then the large mass is at a downward, at a negative potential. So the total potential energy of the system V is negative of 2m gz, right? And then of course the other two masses are at zero potential, so we have negative 2m gz is the total potential energy. Okay, so then z we can replace. So we have the formula for z, so this is negative 2 mga sine theta, and that is what we have. So from here we see that the total energy, the energy of the system is given by ma square theta dot square. This is the kinetic energy plus minus 2 mga sine theta, and this is equal to E, the total energy, right? Okay, so then we have that at theta equal to 0, we have the initial condition, the masses are at rest, so theta dot is 0, velocities are 0, right? And we plug in, so at theta equal to 0, we plug in all these quantities here. At theta equal to 0, we have theta dot is 0, so we are going to get that the energy is 0, right? So this is the energy at t equal to 0, and energy is conserved for the system. From here I plug in this information, I get that theta dot comes out to be 2ga sine theta, 2g, well, there is an a square, so 2g by a sine theta. Okay, so that is what we have. Okay, then so that is the energy conservation of the system. Okay, so this question now is, let us add another small bit of information. The second question that says is, find the second part of the problem, find the time elapsed when the sliders collide. Find the time elapsed when the sliders collide, and we see that theta dot is 2g by a times sine theta. Well, everything is under square root here. So we have to find the time elapsed when the sliders collide. So when is the slider going to be colliding? When? So this happens when theta is equal to 90 degrees. Right? Remember, let us go back to the diagram. When theta becomes, when this distance x goes to 0. When x goes to 0, this happens when x goes to 0 or theta becomes 90 degrees, right? So that is when we have to find. Now, from this conservation principle, we have the following relation. From here, I can find what is the total time. The time t is nothing but, we are inverting this relation to an integral form. So this is a divided by 2g times dt by sine theta. Okay, so that is what we have, and we get that this is 1.85 times square root a by g, and this is where the sliders. So what have we got here is, we have to put theta from 0 to 90 degrees. The time at which the sliders collide, and we get the following relation, and that is what it is. Okay. Okay then. So, so what have we got? I think the problem is done in terms of we don't have any more parts in the problem. We have new problems for with these ideas, which I shall be discussing in the next module. So thank you so far for listening.